Sorry. All right. So for the people at home, I'll just do a small rewind. Am I muted? Wait, this is. No, I'm not muted.
You're not supposed to be walking.
Can the people at home hear me? Type in the chat. Okay, no, great.
Oh, speak a little bit louder because this mic is not present.
All right, gotcha. So I'll do a little rewind. Let's see. So I'll do a brief rewind. My name is Milan. I am a red teamer and a penetration tester at a company called Cilynx. I've been doing this for quite a few years now. Today we're going to talk about smuggling. As I've told the guys here, we're going to talk about types of smuggling, the classical ones, the modern ones, and we'll also give some real life examples of some mind-boggling hacks. So I'll start with a little description about HTTP. So if you want to actually understand how smuggling works, we need to understand how HTTP works. And we'll start with the most prevalent protocol nowadays, which is HTTP 1.1. This protocol basically has a few components. Now, the real important one is the first line. Now, the first 6 lines are actually headers. Now, what is interest of us is actually the URL in the first, the actually host, which means where we want to send our HTTP request. Like when you enter Facebook, this will have facebook.com, what type of content type we have, and how big is our actual request. We'll get. But basically, every HTTP request of the one family will look like this. Okay, they may be bigger, smaller, more headers, less headers, but in the end, all will have the first line, which is like the URL, and the second line, which is the host. All the rest are configurable. Now, let's get deeper. So, if you want to talk about smuggling, what we want to actually talk about, and I'll go straight ahead and talk about smuggling. Now, I'll show you this slide. I'll go back and I'll return to it. But basically, what we're seeing here, we're seeing on the left, we are seeing a request. Actually, we're seeing 2 requests, okay? But what smuggling is, basically, is that one person sends these 2 requests, okay? He sends these 2 requests, and the server thinks the front end, and I'll just go to the actual graph. Look at this way. A normal user sends a request. Okay, an HTTP request that looks exactly like this. Okay, everyone's sending their request. Like let's say Facebook. Let's say you have 1,000 users on Facebook right now, like a million or maybe 100 million, and everyone is sending their requests. Now, an attacker can also enter Facebook and send his own request. The thing is, the HTTP smuggling attack, as the name implies, allows us to smuggle additional HTTP requests. So while a regular user sends, like, say, these blue requests, an attacker sends his original request appended with some injected HTTP. So what happens is the front end, okay, which is in the classical architecture, let's say you enter Facebook, your host is facebook.com, that's the front end. Behind the scenes, if you want to see like the list of friends of someone, so it will be tunneled from the front end to specific backend that handles such requests. And these requests are put in line. What do I mean in line? The classic HTTP protocol is stateless. What does it mean? Well, it means that basically every new request is a new TCP connection. Now, when you connect to Facebook, your browser creates like, and I'm not talking about WebSocket, okay? I'm talking about classic HTTP right now. When you enter Facebook, what happens is your browser creates like 100 connections for every new request. Now these requests are going to the front end. Now, the front end has a connection to the backend. Now, this connection is a session, is a TCP session. These are usually not every single request is going to create a new connection between front end and backend. No, basically, it is just one session that has requests streaming. Okay, so the backend has just a humongous stream of data, like millions of requests, and it needs to know where each request ends, like where is Milan requests end and Katie's request start, because as far as the server knows, unless said otherwise, this is all one big request. So 1,000 people need to be 1,000 requests. So how do we actually differentiate when a request starts or when it ends? So in HTTP 1.1, there are two ways to do that. Now, there is the content length and there is the transfer encoding. Now, what are these? Let's look at the request in the left. Okay, you can see a post request. Post means I'm sending you some data to the find URL at mysite.com. Now you can see in red, there's something called content length, and it says 13. What 13 means the data I'm about to send you is 13 bytes big. Once these 13 bytes are over, well, my request is done. Whatever comes next is somebody else's request. So the counting is actually like this. Like the Q equals smuggling, that's 11 bytes. And you have /n/r, which is according to the RFC of HTTP 1.1, is basically a new line. So they are counted. Each one of these is a byte. So we have content length. Okay, cool. And we have another RFC specifications called transfer-encoding chunks, which is just a different and more complicated way to do the same. Chunk encoding, as the name implies, is sending chunks. Now, each chunk is prefixed by its size in hex. Like 11 in hex is B, because you get to 9, there's no 10 in hex, there's A, and then there's B. So 9, 10, 11. And the data, what you're actually seeing here is like it says, okay, look, this request is based on transfer encoding. This chunk is 11 bytes, and the next chunk is 0. When you say 0, you mean, okay, I'm done. Like, no more chunks. Like, that's it. So you have two different ways to say when a request ends. Okay, cool. What can we actually do with it? Well, we can fool the server. Let's say you have the front server that looks at content length. Okay, and the back end looks at transfer encoding. That's a problem. Now, how can this happen? It happens all the time. You install a new server, it can prioritize either transfer encoding or content length. You can configure it any way you want. And sometimes the front-end developers go for the content length, sometimes transfer encoding, etc. So if you can create a request that actually has content length and transfer encoding, what will happen? The answer is HTTP smuggling. So how does it actually work? We can look at this request. Now this request may look a little bit strange. It has content length and it has transfer encoding. We can look at this from 2 points. If we look at this as a content length, if we, for a moment, just forget there is a transfer encoding, well, let's say, okay, there's content length here. Well, it says 3. So /n/r and 8. That's 3 bytes. So if you're looking at the content length, you say, okay, the request is actually ending at 8. This is the end of the request. Whatever comes after that, not me. But if you look at this as a transfer encoding, you say, okay, here's a chunk of 8 bytes smuggled, 8 bytes, and 0. So the actual request is the whole, like the whole 8 smuggled 0. So if you look at content length, it ends at 0, at 8. If you look at, well, transfer encoding, that's the whole request. So what happened if the front end looks at transfer encoding and the back end looks at content length. What happens is something very interesting. The front end takes the whole request because it's transfer encoding, it sees all of it, and it passes on to the backend. Now the backend looks at content length and said, okay, so until 8. So here's the request, the first request I received. Now this smuggled, that's the next request. So once an attacker sends such request, the next request of anyone that will come in line, because there's a socket between front-end and back-end, and all the requests are in line, what happens is this smuggled text is get prefixed to the next user request. So the next guy after me gets his request look like this. Now, if this is the request the server gets, it will just return the Garlic error, like what is smuggled get? This is not HTTP protocol, right? But we will get there. Now, here's a different situation. Let's say the front end is actually looking at content length. So it says 13. Now, all of this text is 13. I mean, from like this 2, this 1, etc., until smuggled, this is all 13 bytes. Now, if you look at this from a transfer encoding perspective, this is an empty request. There's only 0. There's nothing here. So if the front end is content length based and it received this request, it just moves it on to the backend. But the backend sees this request and says, okay, here's one request, 0, and here's the start of the next request. So basically, this is just the reverse of the first example. Like this one is looking at content at transfer encoding. The second one is just looking at content. The key here is to give the front end the full request, and the backend will need to see the request spliced in 2. But we'll get to examples. There's one additional case which is very interesting. What if, let's say, both front-end and backend support transfer encoding? Now here it gets interesting because you basically front-end can support content length. It can, but it will prefer transfer encoding when presented with one. So how can we actually make the front-end look at content length, but the backend to look at chunk, at encoding, or vice versa? How do we do it? Well, we can make, let's say you have 2 servers, okay? Let's say one server gets transfer encoding X, and it says, okay, the second server gets 2 headers. You can do that. You can duplicate headers, you can send it to the server. Question is what the server will do with them. Now, some servers will look, okay, so transfer encoding X. The last one is the one I'm going to look at. What is X? I don't know. It's a legal header. I'll go with content length then. The backend, let's say, the front end will look at the first header and say, okay, the first one is valid. So let's say Apache will look at 1 and Nginx will look at the second. So the goal here is actually to fool the 1, but make the second one still see the transfer encoding. So there's a lot of games here. You can duplicate headers, you can make here some noise, spaces, X, etc., all sort of tricks until one of them just says, okay, there's no content, there's no transfer encoding here. I quit. This is a content. So once you do that, you basically reverse them to one of these situations where one of them is content length and the second one is transfer encoding. That's a bit more complicated, but basically just does the same. Now let's move one more. Okay. So what can I actually do with smuggling? Like, what's the damage? What about it? Okay, so let's look at the request content. Now this is a content length of 313, and all of this red text is actually the body. So it gets to the front end, and the front end is like, okay, cool. This is a whole request. I'll move it to the backend that supports transfer encoding. Now the backend looks at this and says, okay, this is 0. This is just an empty request. I'll just move on. And this is the next request. Now let's look at this request for 1 second. It's a bit verbal, I know, but this is like a real life example. What we're seeing here is a post. Okay, like let's say you are in a website, WordPress website, something like that, and you want to put a post, a comment, you've read something, an article. So all of that gibberish, there's one parameter called comment, and it equals 1. If we take this request and send it to the website, there will be a new comment by the name from the user we, with the email we.com, whatever, and it will say 1. This is the original. Now what the attacker is doing here, he is actually saying, okay, here's a request and I'm smuggling this. Now on the backend, the backend will say, okay, this is whatever, I have no answer to this. This is an empty request, I don't know what you want from me. This is the start of the network. Now the guy after me that enters the website, as we discussed earlier, his request will be actually appended to the last parameter, which is 1. So what will happen is, I am the attacker, will see, or anyone, depends on the website, will see a new comment from the user we, email, whatever. Its content will be the request of the next user, and including cookie session. Basically, this is an account takeover. And it is nice. Okay? In 2017, like it was everywhere. Like this vulnerability was literally on all bug bounty programs, and it is still prevalent today. Tesla got one like 10 months ago. No, Department of Defense got one 10 months ago. Tesla got 1 year ago. I found one 5 months ago, one of our clients. Like it's still happening, okay? And this is the old version. Now enter HTTP 2.0. Now there is a security researcher called James Kettle. Now he published a very interesting paper. Now all we've talked about right now, this is like HTTP 1.1. This is the old product. Well, actually, it's ancient. Everyone moved to HTTP 2.0, which is also ancient, but that's how it works. So HTTP 2.0 was supposed to be immune, and it is, as far as we know, yes, because tomorrow someone might find something very interesting. But at the moment, as far as we know, if two servers are talking in HTTP 2, we can't really smuggle anything. But reality works a little bit different. What do I mean? Let's say you are on CloudFront, Akamai, like whatever, okay? And these WAFs are very advanced. And by default, nowadays they support HTTP 2.0, okay? So that's nice, but my ancient server does not. That's nice that Akamai has moved to 2.0, but no one asked me, and my server does not actually support it. So what do we do? Very simple. Akamai would talk with the customers via HTTP 2, but to me, it would talk via HTTP 1. Everybody wins, right? So here's the thing. This is actually what I've just explained. So we have like WAF and frontend, HTTP 2.0 gets the request, but on the backend, still HTTP 1.1. So what are the actual risks here? Like what can we do? So before moving on, let's talk a little bit about HTTP 2.0. There are some key differences. Major one, this is a purely binary protocol. What does it mean? HTTP 1 is string-based. You can just open Telnet, connect to a web server, type get/HTTP 1.1, and you will get a response. Now, what happens here? Telnet, text, and it works. HTTP 2.0 is a little bit different. It's purely binary, it's all hex, and you can't do it with 2.0. What happens nowadays is most libraries just support it. You developers still use write headers, etc., like they're in HTTP 1.1, but behind the scenes, the library just converts the request into HTTP 2.0. So once again, everybody wins. But there are a few things. Now the headers in HTTP 2 are different than HTTP 1. Let's get into examples of real hacks that James demonstrated from his programs. Now, take into account that these vulnerabilities are out there, just hanging. Now, just that you know, organization, statistically wise, there are around 1,100 domains in all public bug bounty programs. Now, that's a drop in the bucket. You can simply imagine that everybody else is just whatever, like you don't know what's in there. So let's get to it. So who got hacked by HTTP Smuggling 2.0 and how? That's the more interesting. Let's start with Netflix. Okay. So let's talk about HTTP 2.0. There is something called RFC. I'm sure we're all familiar with it. Basically, it's just like, please do this, everybody. Don't deviate. Like we have headers, so please use headers. There's like a host header. Please, everybody use host header. Like this is the most Wild West you can get, because even Netflix does not follow that. Not Netflix. The next target does not. We'll get to it. Let's talk about, so the content linked header. Let's look at the request on the left. Now, this is an HTTP 2.0 request. This is how it actually looks. It's a little bit different. It's translated from binary to text, okay? But that's okay. So what James did, he actually added, now these are headers. So he added the content linked header. Now, HTTP 2.0 does not really need it. Like, the header has its own built-in sizes, it's called frames. But you can, according to RFC, append the content length as long as it is current. So that's what he did. And this is the actual body of the request. Now, once again, it looks very similar to the classic HTTP one. But if we look at the content length, we can understand that all the way up until here, that's content length based. Whatever next, this is like the next request. So what happens is the front end of Netflix translated the HTTP 2.0 request into the classical HTTP 1.1. And what we get here two requests. So first one with the content length of 4, which actually ends here. This is like 4 bytes. Content length 4 bytes. This is the next request. That's nice. And what we see here is get and a host. Now, this is a trick from bug bounties. Basically, when your browser sends a request to a server and it specifies a host that, let's say, not a Netflix, the server will just drop it. It says like, okay, you either want Netflix, our subdomains, or services. Like, if I put Google in here, Netflix is going to say like, what am I, a router? Like, no, drop by. So there's a trick. Now, 02.rs is actually a host name of a James server, and this little question mark, and then Netflix.com. This is a regex bypass, basically. So Netflix is okay. He actually wants to go to Netflix.com. In this situation, what Netflix returns is a redirect. So let's say you want to go to, tv.netflix.com, but you actually go to www.netflix.com. You will get a redirect to tv.netflix.com. So by appending this request to the next users, Netflix redirected every user that got this prefix into the server of the researcher. Just like the post, but into RC2. So every request of every user that got it got redirected. Now you can automate this, and pretty much all the users eventually will enter. Realistically, you're not going to do it, but you just might as well do it. And more interesting thing now, there's something called JavaScript. For those who don't know, this is basically like the code equivalent of HTTP, of browsers, basically. Many times, website calls JavaScript externally or from other directories of this domain. So let's say if Netflix has a special folder that hosts all of its JS files, the browser will want to get them. Now, if the request that wants to get the JS gets prefixed with that, it will go to look for the JS on the evil host. And then we'll wait the JS, but it's called XSS. Sure, most of you know what it is. Basically, he could send JS files to all Netflix users, still a cookie, keylogger, screenshots, whatever. Can't take all of this. Because this JavaScript will run in the context of the site. Okay, so that was Netflix. Yes, yeah. At this case, yes. Usually, you can configure anything, but usually, host will redirect you to its subdomains. Now, this is not RFC or something; it's just the way people do it. Okay, but so if he would put here like just 02 RS, Netflix will just drop it. Like, I'm not Googling that. Go to RC whatever yourself. But since it's a service of Netflix, it will redirect. Okay, so this is the trick because the Netflix looks at the end. But if I put this question mark into the browser URL, I will actually get redirected to 02 RS. Okay, so that's Netflix. Amazon load balancer. That's a small service. Now they practically implemented HTTP 2.0 somehow without really regarding the RFC, as I've mentioned before. Now the RFC states something like this. You cannot, any message containing connection-specific header must be treated as malformed. If you put content transfer encoding in the request as a header, this is a bad request, drop it. That's what RFC says. Amazon says, nah, just give it. And what happens next? Well, this is very similar to the classic one. Basically, you say, okay, this is transfer encoding, 0. So you translate it and it becomes first request, nothing, 0. And then a new prefix, okay? Not evil.net just for the sake of it. And what happens here is people, this is a good one. Like this is an example. Just as follow-up to your question, if I remember correctly, here was not an AWS domain, and it's still redirected to it. Okay. Now this is a matter of implementation. Netflix, drop. AWS, go. But I need to check this out. So what happens is the request of users once again passed to the C2. This time he just used transfer encoding rather than content length, and this time it happened because no one actually looked at the RFC. I had to read the RFC just to make this presentation. And what happens next is all of the requests of the users are moved to evil.net, and there is something that's called a referrer. Okay, there's something called OAuth, which is an interesting implementation of authentication. It's a whole different lecture on itself. But what's important is it passes your credentials inside one of the headers. So if my C2 requests server receive requests from users who did OAuth authentication, I can see the actual token. So authentication stealing. AWS load balancer, all the websites on AWS load balancer were vulnerable. Okay, so there's that. Next, Jira. Now this is a really interesting case, a funny one actually. Jira, as you all know, is a ticketing system. Like there's like a million memes about it. No one likes it. for some reason. Anyways, here's the thing. The case here, and what happens is you put an arbitrary header, like full, whatever. You put full, you put bar. Now, if you remember, I said something about /n/r. These are the terminators in HTTP 1.1, line terminators. What happens is, in HTTP 1.1, if you see /r/n, it says, okay, this is the end of the line. Whatever next is a next header. Okay, so that's another trick. Once again, this is HTTP 2. Gets translated to HTTP 1.1. But here is something interesting happened in Jira, which was quite unexpected. So he got his request translated into 2 requests. But the thing is, he forgot to remove the /r/n in his second request. So what actually happened, he smuggled the request, but it was not prefixed to anything, because according to HTTP 1.1, /r/n means, okay, that's the end of the request. They actually got 2 requests, like one, the original, and some smuggled request. They got 2 requests. Okay, that's okay. So what about? He got the response only for the first request. The second one got stored. And what happened is, the next guy that sent the request got the response of the smuggled request. And his request got stored. Came third person, same story. Okay? So he sent 2 requests, and he got response for the number 2. 3 got stored. Next guy sent his request, got response for 3. And the response for this guy got stored. 5th guy came, wanted to respond to 5, but got 4 because that was in queue. What happened is the whole site got out of sync. People got cookies of other users. They pressed something on Jira and got logged in as someone else from some other company. And Jira had to actually, well, after the patch, they actually had to revoke all sessions because people just got logged in into like not their organization. This is crazy. The site was one request, like the guy did 1 request. That's all, and everything fell down like a house of cards. That was Jira. And so there's that chaos. And this is it. Mitigations. How do we stop this? Now, before thank you, regarding the mitigations, look, all of these problems come from the translation. Like, yeah, you can say just don't do it. Don't translate from 2.0 to 1.0, but let's be honest, it's there because people. Okay? You can be right or you can be practical. So practically speaking, listen to the RFC. Let's begin with that. Don't allow semicolons, all sort of special characters, etc., /n/rs in the headers. Dump them, they are malformed. Problem solved. And this is it. Now, imagine how many websites out there actually vulnerable to such an interesting attack. This is pure logic. Like, this is, I think, it's mind-blowing. But this is it. If there are any questions, I would be happy to answer. Yes.
With the mic. Yes, possibly with the mic. I'll get the mic to him. You stay here so everybody can hear the question.
Yeah, okay, so using the first example, the first one using the 1.1, and if I smuggle a request, should I see the 2 responses? Should I see 2 responses?
Okay. Well, can you hear me?
Yes.
Okay.
Oh. Okay, I'm asking because a colleague of mine and me found a couple of HTTP request smuggling.
Nice.
In different clients, and in every scenario, we saw two responses. And two responses related to the smuggled request. And I wasn't sure if the smuggled request really, if another request was sent or just come back to me. And if it has any impact, or maybe if I can, if it's not really a smuggled request and something else, maybe if I could use it in order to get into sensitive sources or something like that.
Right.
Thank you.
Okay, gotcha. Look, the best way to check for smuggling attacks today is blind time-based. If you send, let's say for this first example, if you send a content length of 5, it says 3, but if you send 5, actually no, you need to send like, let's say 12, 100. Okay, if you send a request of chunks, okay, you need to change the 8 to 12, let's say, and send it. Now, if you get a timeout, it means that someone somewhere expects for the rest of the chunked request. That means that the backend is using transfer encoding. Now, if you don't get that, then you probably don't have smuggling. Now you can use error-based, but mostly you just don't get any feedback from my experience. So time-based is always working. It's blind. You can't hide it. If you get 2 requests in response, I don't think, if you send 2 requests and they are regarded as 2 requests, I have not met such implementation. So I can't really answer, but you can run Turbo Intruder if you're familiar with the tool in the purposes. You can try and smuggle prefixes, and choose like some API you absolutely know exists, and see if it works. But if you receive 2 responses to 2 requests, it does not look like smuggling. It looks like there's a tunnel, full tunnel on the backend. But again, I'm not familiar with this case. Might be worth checking, but blind approach would be good, and intruder. If these both don't work, then I'm pretty sure there's nothing to look at there. Okay. Hope that somehow answered your question. Once again, I need to check. I need to see this special case. Any more questions? Yeah.
Just have like 5 minutes if we can make it quick.
So isn't the mitigation should be like a default server configuration? That's it.
Now, default is not good in our case. Why? Because the default, let's say for server A, is chunked, transfer encoding. I prefer transfer encoding. The front end, content length, default. You have 2 vendors, like I had CloudFront, which is Amazon, and whatever backend was there, both were on default, and there was smuggling. So the thing is, you have either misconfiguration on. You can have a misconfiguration. You have one configured to do A, and it's default, and this backend uses B, which is its default, and that's how you got the vulnerability in the first place. So the recommendation is to sync between them. Now, if we're talking about HTTP 1.1, if you create a new TCP socket from front end to backend, or you just do it in HTTP 2.0 all the way, this is a good recommendation. Or third, you just put both of them content length or transfer encoding. You see, this is the recommendation for 1.1. And that's about it. So thank you, guys.
Thank you, Milan. If there are any questions in the chat, so please go ahead and send them to me or relay them on, and we can pass them to Milan, and he can get you